Bonjour à tous. Hello everyone. So this is my PhD work. I'm in second year. Um, this is what my PhD is about. It's about clustering radar data. So I would like from the data coming to my radar to be able to cluster the surroundings of the radar according to the nature of the clutter. So to begin with, I just did the clustering in one direction. So for example, if I get the information coming back from this direction, I would hope that my clustering algorithms will give me two clusters, one with C clutter and one with ground clutter here. So here is a plan of my presentation. First, I will present the data and the mathematical problem. Then I will present the modelization and the geometric representation of the data. And finally, the clustering algorithms. So to begin with, the data and the mathematical problem. So it's very simple basics about radars that I present now. So the radar emits a radio wave, and it's reflected on the environment and comes back to the radar. And the radar records complex numbers, which modulus is the amplitude of the signal received, and which argument is the phase of the signal received. So this is for what I call one cell. It's kind of a unit zone of my surroundings in one direction. So after a pulse, which is a signal emitted, the radar records a series of complex numbers. So it first records a complex number corresponding to the closest cell, and then to the cells that are far from the radar. So for one pulse, I record a series of complex numbers. And in one direction, the radar will emit a pulse, which is a series of pulses. So in one direction, I will record a matrix of complex numbers. So each line corresponds to a pulse, and each column corresponds to a cell. So we can think that as the horizontal axis is like the distance axis from the radar, and the vertical axis is the temporal axis. So what I would like to do now is to cluster this data, and what I would like to cluster is the cells. My one data will be one column of this matrix corresponding to one cell of the environment. So the kind of information I would like to extract from this columns, from these vector columns, is kind of same kind of information than the spectrogram that we can have through the Fourier transform. I will present this after. So here is a mathematical problem. I have two cells, so represented by two complex vectors, and I would like to know how different are they. So I would like to represent them in a metric space in which the distance between those two vectors will be how different is the nature of the clutter. So I will now present the model and the geometric representation of the data. So we did some assumptions about the signal. We assume that the signal is stationary with zero mean, and it's an autoregressive Gaussian process. We have an equivalent vectorial formulation, which is this one, that my vectors are an autocorrelation matrix times a complex random vector. So this is this complex formulation I use when I want to simulate some data. And I just add a noise coming from the radar. And so we just have something specific due to the assumption of stationarity. We have that it means the autocorrelation matrix is a Toeplitz matrix. So Toeplitz means that the coefficients on each diagonal are constants. So this is one of the important slides of my presentation, introducing the metric I will use on my data. So I assume that each of my vectors are realization of a multidimensional normal law with a certain kind of covariance matrix. So with information geometry, I can compute distances between parametric laws, like the normal laws. So what I did is, for each vector, I tried to estimate the normal law where it comes from, and then I compute distances between the corresponding Gaussian laws. So there is a first part, which is estimate for each vector the corresponding Gaussian law, and then compute the distances between the Gaussian laws. So for each vector, I will represent it by the corresponding covariance matrix. And then I will compute distances between the normal laws using the information geometry metric, which comes from the Fisher matrix, defining the local scalar product. So this is classical information geometry. Then with this local scalar product, we can, this is the application for normal law in dimension 1. This is the corresponding scalar product. With this local scalar product, we can define geodesics and compute the distance between 2 points. So this is Riemannian geometry. So what I have now is for each vector, I have a corresponding autocorrelation matrix. And I can compute distances between this autocorrelation matrix. But for my computation, I use another space to represent my data, which is this space here, P0, mu1 to mu n. So it's in R plus star times dn minus 1, where d is a complex unit disk. So for each Toeplitz Hermitian definite positive covariance matrix, I have a point in this space. What does it mean, the point in this space? We can understand them, the meaning through this theorem, which says that if we assume that the Toeplitz Hermitian positive definite matrix is the correlation matrix of a stationary signal, then its coefficients in D-1 are the coefficients of an autoregressive model. So the information here is the information corresponding to the coefficients of the autoregressive model. And P0 is just the mean power of the signal. And why do I do this transformation from one space of representation to the other? It is just because the corresponding metric in the other space is simpler. It's just a product metric. So this is the explicit formula. And it's better for the computation to have many space of dimension 1 and to do the computation independently in each space than to have one big space. For example, if I want to compute the average between 2 points, I just have to average each coordinate or each coefficient. So it's easier. So this slide is just to show that my space of representation for my data is a good space, splitting well my data. Here what I did is that I simulated 2 data sets with 2 different autocorrelation matrices. I represent them in my metric space. And then I did a principal component analysis, but it's not possible to do it or not meaningful to do it directly in my Riemannian manifold because it's not necessarily a vectorial space. So what I did is that for each point, I wanted to represent it in the tangent space at the mean. So first, I compute the mean of all these points in my Riemannian manifold. Then, for each point in the Riemannian manifold, I associate a point in the tangent space at the mean using the logarithm map. Then I do, because the tangent space at the mean is just a normal vectorial space, I just do a classical principal component analysis in the tangent space. The data are not splitted like this if I just use directly the columns, because they are both data sets are Gaussian laws or normal laws with 0 mean, so they are not splitted like that because they are both 0 mean. So now I will just present the clustering algorithms I use. So what I did about the methodology is just is I simulated 2 data sets with 2 different autocorrelation matrices, let's say R red and R blue. And then I give both data sets to my clustering algorithm, and I expect my clustering algorithm to group together the points simulated with the correlation matrix R red and to group together the points simulated with the other correlation matrix. So here I present the k-means algorithms, which is the first one I use. This is not real. This is not my data. This is just Euclidean data, just to present the algorithm. So what we do in this clustering algorithm, for example, here, if we want 3 clusters, we just pick randomly 3 points in my data sets, and I will call them barycenters. So I pick 3 points, I call them barycenters, and then there is a loop, and the first step of each loop is to assign each point of the dataset to the closest barycenter. So that's why there are red cross close to this red cross, and blue circles close to this blue circle. And then when I assigned each point to the closest barycenter, I compute the new position of the barycenter of this cluster. The barycenter in a Riemannian manifold, or the mean, is defined for me as the point minimizing the sum of squared distances, and I estimate the position of the mean of each cluster doing a gradient descent on this function. So I need only 2 things to do the K-means algorithm. Is I need a metric to be able to assign each point to the closest barycenter, and I need to be able to compute the mean of points. Okay, so this is just visualization of some results. And the other clustering algorithm I used is the mean shift algorithm. So here I have some data points I would like to cluster. The first thing is to estimate the density function of these points. So for this, I use a kernel function. And then each point is going follow the gradient of the density function and just ends in a submit of the density function. So here the difficulty in this algorithm is to find the good size for the kernel function. The smaller is the kernel function, the more irregular is the estimation of the density function, and the more there will be clusters at the end. Okay. So thank you for your attention.
We have time for some questions. Yes, please.
Could you give the details how you map the positive definite covariance matrix to the coefficients?
Can you repeat the question first, please?
How you map that covariance matrix to find the coefficients that map to the...
Yeah, it's this slide.
Yes.
It's a recursive algorithm that I use to do this transformation. There is an algorithm called the Levinson algorithm, but it's hard to explain it.
No, it's okay. It's for Toeplitz matrices. Right.
Yeah, it's for Toeplitz matrices. Yeah, it's Toeplitz Hermitian definite positive, and this is a bijection.
Yes,
but with my data, I just have my basic data, and I compute directly these coefficients with an algorithm called Berg algorithm.
Berg, okay.
Yeah.
Berg.
Yeah.
Okay, good.
One more question? No, let's thank